Dear students, I would like to welcome on my next course, which will be carried out online. We have no more possibility to meet, so I hope that this way of the presentation can help you to understand the basic facts about the thermodynamics and heat transfer. Today I would like to open the new chapter, which is called the water heating. The basic question is, what is the steam, what we can say about vaporization, condensation, and so on. Just to understand this topic, I would like to start from the beginning. That means from the questions, how we can create a steam. Imagine the following situation. You will have a container which is filled in by the water. The water has a temperature 20 degrees of Celsius. Please look at these graphs and I would like to tell you what can happen. We start from the point 1 and now we supply the heat. Due to this warm-up process, we increase the temperature. And the heat which is needed, it's called the sensible heat. You can calculate it very easy if you take into account the temperature difference multiplied by the heat capacity. We supply the heat up to the point 2. If we reach the point 2, we call this point as a temperature of the boiling process, which for the 1 atmosphere correspond to the 100 degree of Celsius. This point 2, it's called the saturated liquid. This is just the last point at which the water can be in the liquid form. If you continue to supply the heat, the boiling process will be starting. What can happen? You still supply the heat and you will observe that some small portion of the liquid will be evaporated and the gas will be created. You still supply the heat up to you reach the point 4. The point 4 it's called the saturated vapor or steam. This is last point at which the all liquid, saturated liquid in the mixture will be completely evaporated. And now you have in the container only the gas. If you still continue to supply the heat, the temperature will be rising again. And you reach so-called the point 5, which we call the superheated vapor. This process, which I now describe, using the lines or using the points that are lying on these lines, it's called the water or the vapor or the steam generation. This is so-called the isobaric process. That means, please keep in mind, we are talking about the isobaric warming process or isobaric evaporation. This is the typical case which you can find in many applications in many engines. Particularly, if you look what can happen between the point 2 and 4, this is not only the isobaric process, this is as well the isothermic process. That means if we will be talking about the evaporation or the condensation, we keep in mind that this process is isobaric and isothermal simultaneously. The amount of the heat which is needed to supply between the point 2 and 4, that means for the complete change of the phase, it's called the latent heat of vaporization or the latent heat of condensation. If you, for instance, stop the evaporation in the point 3, you will find that your saturated mixture will be composed from the saturated liquid and saturated gas. The amount of the gas or liquid in this mixture depends on the point where you stop the process of the evaporation or condensation. I hope that it is clear, and in order to understand, we can continue and look at the next slide. This is nothing else as some description of all 5 states which I now describe. We have started from the state 1, from the initial point given by the temperature, 20 degrees of Celsius. We supply the heat and we increase the temperature up to 100 degrees of Celsius. At this point, at this temperature point, the boiling process will be starting. And during the evaporation, during the boiling process, we evaporate the saturated liquid into saturated gas so long that we have only gas in the mixture. After that, we still supply the water or the heat, and in this way, we increase the temperature again up to we reach superheated vapor. This vapor is, for instance, suitable to use it later in the turbine to generate the mechanical work or even the electrical work. Now we look inside what can happen. This mixture between the point 2 and 4 we call saturated mixture. And you should know the saturated mixture is typical two-phase system where the gas and the liquid are existing simultaneously. You have to ask me, okay, how I can define the amount of the saturated liquid in this mixture? Or opposite, how much gas is there? The question can be replied if you introduce the quality of the vapor. Sometimes it's called like the state of the mixture. We use the variable x, which can represent the ratio between the amount of the saturated gas proportional to the total volume, total mass of the mixture. The total mass of the mixture, of course, is created if we sum the portion or the mass of the saturated liquid and saturated gas. For this point, you have to calculate all thermodynamics variables or properties which you needed, like the specific volume, entropy, internal energy, or even enthalpy. The X will indicate that just we are talking about a saturated mixture. Be careful. You cannot do for the pressure and temperature because for the saturated mixture there is only one pressure and only one temperature. Pressure and temperature are independent from the quality of the vapor. To understand, please look once again at this graphical depiction of the phase change on the graphs below. On the vertical axis, you will see the temperature. Horizontal axis represents the specific volume. Point F means saturated liquid. Point G indicates the saturated vapor. All what is between, it's called the saturated mixture. If we now compose the different lines for different pressure, we can see that this line has a form that it's rising up to the critical point, and this first line, which is on the left side of this graph, indicate the points of the saturated liquid. The second line, which is from the critical point in direction to right, it's called the saturated vapor. All what is between, it's nothing else as a saturated mixture. Now we can go back and look at how far we can use the equation for the ideal gas approximation. Maybe you can remember at the first course I warned you that you cannot still use the ideal gas approximation for any gas. There are the strict rules where you can use it and where not. Generally, you should remember that you can sue everywhere where the error will be just lower than 1%. These rules can you apply here as well. And what you can see now, it's just the superheated region of the steam, which is all areas above these lines which indicate the saturated vapor line. Please look at the graphs, it's indicated here. The red region depicts the region where you can practically apply the ideal gas approximation, which you know in the form PV is proportional to RT. And only what you have to know, it's just the specific gas constant, which is 0.4615 kilojoule per kilogram Kelvin. This is just the specific gas constant for the steam. If you calculate the change in this area, in this region, your error will be just below the 1%. And you can apply the theory. How you can see it, there are the big region, just very close to this red region in direction to left. And this number in percentage indicates the error if you apply the ideal gas approximation. And you can see how you move left. This error will be increasing, and the critical will be just in the critical point where the error can reach 330% for the calculation. So high inaccuracy in the calculation, it's not possible and acceptable. So for this region, we will need completely different calculation method. And for us, it's clear the ideal gas approximation is no more valid. Even there is no wonder that the validity of the ideal gas approximation will be ending by the line of the saturated vapor. Why? Because at this point, the condensation starts. And do you know the ideal gas? It's valid only if there will be no phase change, which is no more valid if you just reach the saturated vapor line. So there is a restricted area where you can use the ideal gas approximation. Be careful. If we're still talking about the boiling process, this boiling process depends on the pressure. Generally, you should remember that if you increase the pressure, you will increase this boiling temperature as well. From 0.01 megapascal up to 25 megapascal. However, you can see that this line, that means for the pressure 25 megapascal, it's just out of the critical point. This is actually too much. So the limit is just 22.06 megapascal, which just fit the critical point. If you are above the critical point, this change of between the gas and liquid can happen chaotically, and it's not practical possible to apply in the engines. So all engines, all cycles practically, which we can imagine, the heat cycles, will be working with the pressure definitely lower than 22.06 megapascal. Even 50 megapascal is too much. Just these graphs, which represent the boiling temperature depending on the pressure, can tell us that if we increase the pressure, we increase the boiling temperature and opposite. So you know that if you hike on the mountains, so you can practically boil the water faster because it will be happen at the lower temperature. And opposite, if you increase the pressure, for example, during the cooking, you will actually increase as well the temperature which you use for preparation of the food. The one typical technical application, it's just the nuclear reactor, so-called the pressurized water reactor. You will find the two circuits in this equipment. And what is very interesting for us is just the primary circuit. In the primary circuit, there is a reactor which is used as a heat source. And the water works as the moderator. Moderator means that you will need to change the speed of the neutrons. And the water in the liquid form can play this role. So the water, which is pressurized, is automatically in the state that for the high temperature will be stayed in the liquid form. If some accident happen, just theoretically, and it will be the drop of the pressure, the water inside in the liquid form will be suddenly changed into the gas. Gas is no more moderator for the neutrons, and the fusion process will be stopped. This is the one point of the safety of reactors. And this fact that using the higher pressure or the low pressure, you can influence the boiling temperature, it's used here as well. On the next slide, it's nothing else as a primary and the secondary circuit. I will be talking about the circuit because it's just very interesting from the point of the thermodynamics. Now we look on the primary circuit. So what I told you now, it's a reactor, which is actually nothing else as a heat source. And during the nuclear reaction inside, we actually warm up the water inside. And the pressurizer and the pumps are used to increase the pressure, so keep this water at the higher temperature in the liquid form. That's all. We can continue, and the most complicated form or the region of the vapor is just this saturated mixture. It's complicated because two different phases are coexisting simultaneously. And the liquid and the gas, they have a completely different properties. The question is, how it's possible to calculate the thermodynamics properties just for the saturated area, saturated mixture? We first look at the specific volume. So in the formula, you can see the specific volume, it's proportional to the sum portion of the saturated liquid and the portion of the saturated gas. The specific volume with one line, one line, indicates the specific volume for the saturated liquid. The specific volume for the gas is denoted with two lines. And the X is nothing else as the quality of the vapor. So, in the limits, if X will be 0, it means that there will be no saturated gas, and we are talking about the liquid, only saturated liquid. And you can see the specific volume just will be proportional to the specific volume of the saturated liquid. Opposite. If the quality of the vapor reach 1, the specific volume of the saturated mixture will be just corresponding to the specific of volume for the saturated gas. So it's very simple calculation. Only what you need to know, what will be the saturated gas or the specific volume of the saturated gas and saturated liquid. And this information you can find in tables or in the graphs. And I can show you later. The same, it's possible to see it if you look the specific enthalpy, the specific inertia energy, or even for the specific entropy. Sometimes, even for the enthalpy and entropy, you can use the simplified form. It means please look at the enthalpy. The enthalpy can be calculated similar as a specific volume, or you can use just this last form where you use the enthalpy for the saturated liquid, which one line, and you add to this value just the latent heat multiplied by the quality of the vapor X. If X will be just 1, means that enthalpy, the total specific enthalpy, will be just enthalpy of the saturated liquid plus the latent heat. The very similar, you can do it for the specific entropy, but you shouldn't forget the latent heat must be divided by the temperature in order to have just the entropy. Both forms, you can use it for the calculation, but of course sometimes it's difficult to find the values or the students cannot remember on the correct form of the formula, so I can recommend just to use the very simple form which I have already introduced it for the specific volume. Just try to find the enthalpy, for instance, for the saturated liquid, enthalpy for the saturated gas, and calculate the specific enthalpy for some particular quality of the vapor. Very simple. You could hear as well that I taught you the number x, the quality of the vapor. It's ranging between the 0 and 1. That means it's varying just 0 for only saturated liquid and 1 for the saturated gas. If the x will be just between 0 and 1, it means that two different phases are coexisting in the mixture. And the x can help you to calculate the thermodynamics properties. At the side, you can see that we will be talking only about the specific volume, enthalpy, inertia energy, and entropy, never about the pressure and temperature because they will be constant for any x. I have only mentioned it that sometimes you will need something like the starting values, and you can use for the calculation diagrams or tables. For instance, here below tables indicates just for the specific pressure and specific temperature, they are practically for the saturated mixture the same. That means you define only the pressure or you define only the temperature because they are not independent each other. And you can calculate the volume with one line and two lines. You have already heard from me that one line indicates a saturated liquid and two lines saturated gas. And you can use now for the calculation. In the table, the same you will find it for the enthalpy and for the entropy. If you have a problem to work with the tables, I can recommend to use the diagrams. In diagrams, you will just see it here, the diagrams where you can find the value of the entropy. It's just the horizontal axis. And you will find as well the information about the enthalpy, which is the vertical axis. This red line, this bold red line, indicate the points of the saturated gas. All what is below this line is just the saturated mixture. And please look now carefully on these diagrams. This actually other lines, red lines, which are going down, are associated with the number. For instance, 0.95, 0.90, 0.85, 0.80, and so on. This is nothing else as a X, so-called the quality of the vapor. In this diagram as well, you will see the isobaric lines, which is just the blue lines. And again, they are associated with the number. This is nothing else as a pressure in megapascal, or in this case, bar. And the last lines, which are here, are the green lines. And they indicate actually the intensity of the temperature. So you will find at the diagram any point for which you can automatically read the value of the entropy and the enthalpy. The benefits of the diagram or the advantage is just for the saturated mixture, you can just directly find the enthalpy and the entropy. If you use the table, you will be actually needed to calculate the value. So you will have only these two limits value, and from this you have to calculate the particular value of the thermodynamic properties. It's up to you what you can prefer. To find the value in the diagram, it's very simple. To calculate it, it's a little bit difficult, so I think it makes sense to give you some examples. Imagine the following calculation. The question is, determine the specific volume of the saturated water for the quality of the vapor 0.2 and 0.8 for the same temperature 100 degrees of Celsius. This is a typical case where we can say that the boiling process will be at 100 degrees of Celsius. That means this pressure will be just about 1 bar or about 1 atmosphere, which is 0.1 megapascal. If we now use the table, and the table you will find on the next slide, you first have to indicate or define it just the value for the specific volume of the saturated liquid, which for this temperature you find 0.001044 meter cubic divided by kilogram. In the same line, you will find as well the second value, that means the specific volume of the saturated gas, which is with two lines or with index G, and it will be 1.6729 cubic meter per kilogram. This is these 2 points which you needed. And now, first of all, we will calculate this value for the quality of the vapor 0.2. You use the form which I have already introduced it. That means our specific volume for just this quality of the vapor, it's composed from the two parts. The first is a portion of the saturated liquid and the second one saturated gas. Because you know already the value of the quality of the gas, you can use these two previous values, insert into this formula, how you can see it later, and you will find that the specific volume for the vapor, which is defined by the x 0.2, will be 0.3354 and so on cubic per kilogram. Analogously, you can actually calculate for the 0.8 and use the same values which you have already found in the table. You insert it into the equation below, and now instead of the 0.2 use the 0.8, and you will find it the specific volume is 1.338528 cubic divided by kilogram. So easy you can define the specific volume. And the same, you can use it for the entropy, you can use it for the inertial energy, you can use it for the enthalpy, and so on. But never forget, not for pressure, not for temperature, because they are the same. I mentioned in the table which you will need it for the calculation, so it looks like this one. This is the table for the saturated mixture, not for the superheated vapor. So this table, it's only used for the area where practically two different phases are existing. If you would like to calculate the superheated vapor, you have to use another table, which mostly it's just prepared for the superheated vapor, and you will find completely different values. Definitely in the second table, there will be only one value for the specific volume, for the inertial energy, for the entropy. However, if you would like to use the saturated mixture, you will have to still use two values for the saturated gas and saturated liquid. So if your calculation required these two values, you will be automatically informed that you will be in the area of the saturated mixture. And I indicated here that because I defined before that this process will be at the 100 degrees of Celsius, you will find at the practically at the first line, this 100 degree, you will see the pressure will be just 0.10135. And now the next, it will be indicate actually the specific volume for the saturated liquid and the specific volume for the saturated gas. This is these two values which you will need it for the calculation. I hope that you understand this problem, and now please perform the calculation as well for the entropy, for the enthalpy and inertial internal energy U, and calculate the state for these two quality of the vapors, 0.2 and 0.8. You have to do the same what I have already introduced here. You can use as well the same table, and you will calculate yourself, And please send me your results on my email, you know already my email, until 25th of March 2020. This is your homework, and this is just for me, just like feedback, in order to be sure that you could understand what I just now introduced it. And the next time, I will send you the other information about the vapor. And in the next course, I will as well introduce to you just how to calculate the basic processes in the vapor. Because how you will see it later, there are a lot of change which are different to the theory of the ideal gas. Thank you very much for your attention, and please do not forget to send me your homework. Bye bye.